We have learned that the integral is two things, the antiderivative and the area underneath the curve. So how do we actually find the area underneath the curve? Well, this is climb time, and in this video, we're going to look at Riemann sums and how they are used to find the area underneath the curve. All right, so we learned in a previous video that if we take the integral of a velocity function with respect to time, it will give us our overall change in position from A to B. And A and B would be times. So from one time to another time, we can find our overall change in position if we knew the velocity function and we found the area underneath the curve. So I have a little example here. In this case, the velocity function is a line. And it means that your velocity is going up at a constant rate. This could easily happen if you apply the accelerator in just the right way so that when you accelerated from a red light, that your velocity was increasing at a constant rate. So it's possible this would happen, although at some point you're not going to keep doing this indefinitely because of the limitations of the car and the laws. But over a short period of time, it could look something like this. And so how do we find the change in position, which is the area underneath the curve? Well, we are in luck here. The change in position, which is going to be equal to, and this is going to be 1 second. So this is 2 meters per second. We'll say our units are meters per second and seconds. So I'll say seconds here. And for this one, I'll say meters per second. And so this represents 1 second. This represents 2 meters per second. And so that means we want to find a position from at 1 second minus our position at 0 seconds. So that's your change position. What is the difference in your position from t equals 1 to t equals 0? Your position at t equals 1, your position at t equals 0. That's your change in position. That would be this area underneath the curve. Well, we're in luck because it's a triangle. And we know how to find the area of a triangle. So that's easy enough. So this is also going to be equal to the integral of v of t dt from 0 to 1. Okay, so this is equal to change in position, as we learned from the last video. And it looks like I smeared that a little bit. Oops. And it also equals the area underneath the curve. So it's also equal to the area from area underneath the velocity curve from t equals 0 to t equals 1. Well, that area happens to be a triangle. So I can say equals 1/2 base times height. So you can use regular geometric formulas to find area underneath the curve. And so we know that our base of this triangle, I'm going to call this the base, is going to be 1. And so I have 1/2, 1. And then my height is going to be 2. And so 1/2, 1 times 2. And 2 times 1/2 is 1. 1 times 1 is 1. So I end up with 1. And because it's a change in position, the unit will be meter. So I changed 1 meter in that amount of time. A good way to find units is that you can just multiply the units on the y-axis times the units on the x-axis. And so if you multiply those together, you get your units for the integral, which is the area underneath the curve. So that worked out pretty well because it's a geometric formula. We know it's the area of a triangle. But what if I wanted to find the position from t equals 1 to t equals 2? What if I wanted to find the position from here to here? And if I did that, I would take this up to here, and then I would take it over. And probably what I would be at, if it's a straight line, I'd be at t equals 4. Okay, so I'm sorry, I'd be at velocity before because this is going up at a constant rate. So I would want to find the area underneath the curve right there. And so the idea is the same. It's just that we no longer have a triangle. Now we have a different shape. So a change in position would equal s of 2 minus s of 1. So we're looking for the difference in our position from t equals 2 to t equals 1. And the way the notation would look like for the integral is it would be from 1 to 2 of v of t dt. What it means is we need the area underneath the curve. And it's still area. That hasn't changed. But what's changed now is it's not a triangle anymore. So instead of a triangle, this actually is a trapezoid. So I could find the area of that trapezoid. And so I wonder if I can take a different color here and indicate this right here. And that would be the area I'm looking for now, the area from t equals 1 to t equals 2. But that's the area of a trapezoid. And we do know how to find area of trapezoids. A trapezoid means that you have two sides that are parallel to each other. And so we have that side is parallel to that side. It's a four-sided shape with two parallel sides, and that's a trapezoid. And we do know how to find the area of a trapezoid. This comes up in previous math classes, and it is the average of the bases. So this would be one base here. This would be your second base here, because they're the two sides. They're parallel to each other. And so when two things are parallel to each other, they are considered your bases in a trapezoid for a four-sided shape. So you would say B1 plus B2 divided by 2, that's the average of your bases times the height. That's how you would find that. And so B1 would be the height of this base, B2 would be the height of that base. So like looks like the height of this base is 2 and the height of this base is 4. So you'd say 2 plus 4 divided by 2. And the height is the distance between the straight line distance between the bases. And we know that it's 1. So the height is 1. And so if I simplify that, 2 plus 4 is 6, 6 divided by 2 is 3, 3 times 1 is 3 meters. So it turns out that in the first second, we only move 1 meter. Our change of position is 1. And in the second second, our change of position is 3 meters. So we move 1 meter in the first second, we move 3 meters in the second second, and our change of position from 0 to 2 would be 4 meters. It'd be the sum of those two areas. But you can find the area underneath the curve any way you want. So as long as you have a geometric formula you know, you can find the area underneath the curve. Well, now the question should come up. What do we do if we don't have a geometric formula we recognize? Let's say in this case, we have more of an actual curve. So it looks something like this. And that is a curve and a geometric shape. If it's a quarter of a circle, yeah, you can find the area of a circle and divide it by 4 if it actually is a quarter of a circle. But this is a little squiggly here. See if I can smooth this out a little bit. But maybe it's not a quarter of a circle, and maybe it's something else, and we don't really know exactly what it is. What do we do then? Well, what we can do is fill it up with known geometric shapes. So I can fill this up with shapes and try to just fill up all the area with known shapes. I can use a combination of shapes if I want to. That is totally perfectly allowed. The problem is if you have shapes with sharp edges and you're trying to fill up a shape that is rounded, that doesn't work super well. But what we tend to do is we tend to just use rectangles. And the reason why we use rectangles is because they are simple to understand. So let's say that we actually have known, we'll just say 2 for the sake of simplicity here. So this is velocity and this is time like before. And we'll say that it starts at 0 time and it goes to 2 seconds. And that starts at 2 meters per second and then it goes to 0 meters per second. So how do we find the area underneath the curve? So like I said, we tend to just use rectangles. So we can divide this up into 2 rectangles. So our first rectangle might look something like that. And the second rectangle might look something like, it depends on what I use as the endpoint. So if I use the left endpoint, then it's going to look something like that. And the second rectangle might look something like this. All right, so if I use the left, when I look at the rectangle, if the left part of the rectangle is the part that intersects with the function, then we call that the left endpoint approximation. So Riemann sum is basically an approximation for the area underneath the curve using rectangles. Typically use rectangles. And so it would look something like this. So your change in position is going to equal the area underneath the curve from, we'll say from 0 to 2 in this case, of v of t dt. And this is going to be equal to the area, but it's approximately equal to the area of these 2 rectangles. So I'll say R1 plus R2. So it's approximately equal to those the area of those rectangles, because we can see those rectangles don't perfectly fit inside of that curve. And so that's why it's just an approximation. So the approximation isn't perfect, but it does work. And each rectangle will have a width and a height. So R1 will have a width and I'll have a height. So width times height, or length times width, however you want to say it. The width is going to be a change in x. That width is always going to be a change in x. And then your height is always going to be a function value. So it's going to be the velocity at a certain point. So in this case, our first rectangle, since we're using the left point, is going to be v of 0. And I said change in x, but in this case, this application is actually time, so it should be change in time instead of change of x. So I'm kind of doing it more generally. It's whatever's on the x-axis. But I'll go ahead and change that to time. It's change in time times velocity at t equals 0. That's your first rectangle. Your second rectangle is also going to be width times height. That doesn't change. It's also going to be change in t times, except your velocity is going to be different this time. Your velocity is going to be the velocity at t equals 1. So it's your velocity at t equals 1. Because at t equals 1, this height will represent the height of the rectangle for the second rectangle. And so at 1 second, we plug that into our velocity function and get the height of the second rectangle. So this represents height of the second rectangle. This represents, at 0 represents height of the first rectangle. And we actually know what those are, so I can evaluate that. Change of time is 1 because we can see this is 1, that's 2. And then the height, the initial height, I don't actually, let's see, I do know that's 2, so I can say times 2. But on this one, I don't know what v of 1 is, so I don't know that one actually. So I can say 1, and then I'll just leave it as v of 1 because I don't know exactly what that is. But the point is, if I do know the velocity function, I can find that height, I can find the area of that rectangle, I can find the area of the first rectangle. So I can have the area of the first rectangle, and I have the area of the second rectangle. And that would give me an approximate area underneath the curve. It'd give me an approximate change in position. All right, well, we know that that area is not great. We know that the area is going to be too big because we can see our rectangle goes beyond the curve right there. So we know that's too big. So we know that that's not awesome. And so what would be good is to try to improve on the accuracy of that. So there's a couple different ways to do that. One way to improve on the accuracy of that is to increase the number of rectangles. As we add more and more rectangles, it gets more tedious, but our area gets more and more accurate. And so with the help of machines, if we can break it down into a nice little formula and use summation notation, we can approximate that area pretty well if we have enough rectangles. So that's one way to do it. Another way to do it is to look at not just the left point, but also look at the right point. So I am going to redraw this because I think it's going to be a little messy to do it all on the same graph. So I'm going to try to redraw this. And this time, let's assume it's kind of the same graph here. This time, instead of using the left point, we're going to try to use the right point to create our rectangles. So let's see how that works out. So that means as I go up here, I go across, and then over here, I will have no rectangle because my right point is 0. My y value is 0 on my right point of the rectangle. On the right point of the rectangle here, my y value is there. And so we see that that's worse in many ways. It definitely looks worse because I have no area out of my right rectangle. However, the same process applies in that we can add more and more rectangles and we can get closer and closer to what we actually want. So let's write this in. So change in position. Well, actually, let me first identify that this is the left. I'm sorry, this one. Yeah, this one was the left right here. And so now we're going to do it the same thing, but now with the right endpoint. So I say change in S is exactly equal to 0 to 2 of vt dt. So these things are exactly to each other. Change in position is exactly to the area underneath the curve, the integral, the area underneath the curve for the velocity function with respect to time from 0 to 2. But that's going to be approximately equal to these two new rectangles I created. I also call them R1 plus R2, but I understand that these rectangles are now based on right endpoints, right? So you have left endpoints and you have right endpoints. I don't know if you can see that arrow very well, but right endpoints. And so that's an approximation with two rectangles. It's not a very good approximation, but it is still an approximation. And like before, our right one and right two, we can find them. R1 in this case is going to equal the width times the height. I'll go ahead and write that in, width times height. And the width is a change in time, so that doesn't change. And then the height, in this case, the right endpoint is actually going to be v of 1. And I don't know what v of 1 is, so I'm not going to try to simplify that. R2, if I knew the actual function, what it was, the velocity function, if I had an equation for it, then I can find v of 1. So we assume when we're doing this that we actually either know the heights, we know the y values ahead of time, or we know the velocity function, one of the two. We can't do it if we don't know one of those two things. We either need to know those heights, we need to know where the height is, or we need to know a velocity function so we can find that height. So R2 is the same thing, except it's going to be a change in t times v2, because that's where the right endpoint is on the second rectangle. All right, so what I want to point out here is a couple of things. First thing I want to point out is there's a pattern to this. Change in time, which is a width of the rectangle, will be the same. If you have two rectangles and you're going from 0 to 2, it'll always be 1. So it's going to be 1 for R1 and R2. When we're looking at the left endpoint, it's going to be 1 for R1, R2 when we look at the right endpoint. So the change in time is always going to be the same. It's fixed. And it's very easy to find. All you got to do is take your overall width and divide it by the number of rectangles. That's your change in time. So in this case, our overall width was 2. We had 2 rectangles. 2 divided 2 is 1. So your change in time is 1. I ended up plugging it in here and here. So your change in time is 1 because it's always going to be whatever your overall change in time is for the area you're trying to find, divided by the number of rectangles. So if we had 4 rectangles, you would take 2 divided by 4, and you would get 1/2. Your change in time would be 1/2. The width of every rectangle would be 1/2 if you had 4 rectangles. And it doesn't matter if you're doing a left or a right. Your change in width is completely dependent on 2 things. 1, the overall area you're trying to find, and 2, the number of rectangles. And so change in time is easy to find. The height, we need like I said, we need one of 2 things. We either need a velocity function, or we need to know the actual y values. We need to know one of those 2 things. But what I want to show you is on the left one, we start on the very far left. So we start at 0, and then we end 1 short of the end. So we started 0, and then we went to 1. For the right one, we started at 1 and went to 2. And so that's always going to be true. The vast majority of your y values are going to be in common between the left and the right. Well, that's not true if you have 2, because I guess in 2, you share 1 value, which is the middle one. But if you had 4 rectangles, you would share 3 values between the left and the right. And the left would start on the far left and would go all the way up until 1 shy of the far right. And on the right, you'd start 1 in, and you would do all the y values until you got to the very end on the right. So they share most of the same heights between the left and the right, unless you have 2 rectangles, at which point they only share 1 height. But all the internal rectangles they'll share those heights. So their differences are not huge, but there's definitely a difference between the 2. So the first thing I want to point out is that there's a pattern to this, and that pattern is that your heights will be the same for all the internal rectangles if between the left and the right. But the left one will have 1 different height, and that's the very first one. In this case, it's 0. And the right one will have a different height, and that's your right one. In this case, it's 2. So this one didn't use 2 as a height, and this one did. This one didn't use 0 as a height, and this one did. So this one will have 1 more height on the left. This one will have 1 more height on the right, and all the ones in the middle will be the same. All right, so the first thing I want to point out. So second thing I want to point out is we know that the area is too big for this one, and we know the area is too small for this one. So we can actually write that in as well. And let's say that the change in position, the overall change in position, is going to be less than or equal to this one, because this one's too big. And so this one was the left. In this case, keep in mind, this is not always true on this specific case. Change in S will be less than or equal to the left, the rectangles from the left endpoint. and then it'll be bigger than or equal to the right. So in this case, it can be sandwiched in between these two values. So if you find it on the left, you find it on the right, you know the actual area is somewhere in between. So let's say you find the value that's too big and find the value too small, you know your actual areas in between. So one thing you can do is you can average those two together and find something that's kind of in the middle. So you can average your right and you can average your left together and get something that's pretty close to the overall change in position. And so that's one way to do it. Another way to do it is to, instead of using the left and the right, use the midpoint. The midpoint is going to be right in between, and use the midpoint to come up with your height. And the advantage of the midpoint is that, and I will try to draw this one here, that if you use the midpoint as your height, maybe that's a bad example. Let's do it here. You use the midpoint as a height, you can see that part of the area would be too big and part of the area would be too small. And you hope that those two areas kind of cancel each other out. So the midpoint would be for sure the closest. It would be closer to the actual area than the left and the right. So you can find the right endpoint approximation by finding the area of two rectangles or using the right endpoint. And you can find the area using two rectangles with the left. And you can average those together and get a change in position that's pretty close. Or you can use the midpoint, which is a little trickier to calculate initially, but then you only have to do one calculation. And that's going to be pretty close to the actual change in position as well, because as you can see, and maybe I will try to color this in a little bit so you can see what I'm talking about. You can see some of this area is too big, and then some of this area is too small. And so if that area cancels with that area, then approximately the area underneath the curve from here to here under that curve should be kind of close to this rectangle, because this rectangle is a little too big in spots, it's a little too small in spots. Those two kind of cancel each other out. And so that's the idea behind the midpoint. So we can find the midpoint. We can use the midpoint of every rectangle and use the y value to find the height of the rectangle. Again, we're still finding the same number of rectangles. We're just using the middle x value for each little subinterval. We're using the middle x value to find the height. And then that gives us the midpoint. We call that the midpoint sum. And that will get closer than the left or the right. But if you find the left and the right separately and average them together, then that's going to be similar. Now, so we can use rectangles because we don't have to have it perfect most of the time. We just need it good enough. In engineering, it's all about knowing what's good enough, because if we're trying to be too precise, that usually costs us more money. So it doesn't really matter. It's irrelevant because time is money too. And so we just need it good enough. We just need the area well enough to get it at the level of approximation that matches the rest of our instruments and the rest of our approximations. So, so you just have to get enough rectangles so that you know the area and you know it pretty well. So if we can use trapezoids and other shapes, and that's perfectly fine. But we generally tend to use rectangles and just use more of them. So if you know a value is too big, you know a value is too small, using the left and right points, as you add more and more rectangles, those two will converge, and they'll converge on each other, and eventually they will get closer and closer together, and you'll know exactly what the area is. So you just have to add more and more rectangles. And eventually, if you have enough rectangles, it doesn't matter if you're on the left or the right, because either one will get to be a good enough approximation of the actual area we're looking for. So that's what a Riemann sum is. A Riemann sum is a way of finding the area underneath the curve through approximations, because we have an actual curve and we don't have standard geometric shapes like a triangle or a trapezoid. And so we have to fill up that curve with standard geometric shapes. And what we usually do is we usually use rectangles. And so you'll hear the term left endpoint and right endpoint and midpoint. And so the left endpoint means that every single rectangle's height is defined by the left endpoint. And that left endpoint is going to intersect the function. The right endpoint is where the right endpoint of every rectangle is going to intersect the curve. And the midpoint would be for every rectangle we create. The subinterval, so this is the overall interval, this is a subinterval. The subinterval, we take the midpoint of that subinterval, and the midpoint of the subinterval is what intersects the function, and that's what determines the height of the rectangle. So that's how we approximate area underneath the curves using Riemann sums.